So let's continue now with the discussion of capillary exchange, which is one of the primary physiological principles that is addressed here in chapter 21. Capillary exchange is, of course, the whole goal of the cardiovascular system. Your cells can't, walk on over to the lungs when they need more oxygen, or trek on over to the kidneys when they need to get rid of some waste products. We need to have a mechanism to do that for them, and that, of course, is the blood. So the blood is going to deliver these things and deliver good things, take bad things away, and do all of those other processes. But in order to do that, we have to have an established mechanism for exchange. And this is, as the name implies, the movement of substances into and out of your capillaries. Now it's going to occur via three methods: diffusion, transcytosis, or bulk flow. Starting first with diffusion. Diffusion, as the name implies, my pen is still working here. Diffusion, as the name implies, is simply that, movement of substances from high concentration to low concentration. But in order for diffusion to occur, the things have to be able to get out of the cell, or get out of the blood and get to your tissues, and vice versa, from your tissues back into the blood. So there are some requirements for diffusion. Diffusion is going to occur either by substances moving between the cells, or through the cells. Now, in order to go between the cells, you've got to be small. Lipid or water soluble. Since you're going between the cells, it really doesn't matter. The only key thing is you're going to have to be small. To go through the cells, on the other hand, you have to be lipid soluble. The only way to go through a cell is to dissolve through its cell membrane. That, of course, requires you to be lipid soluble. And since we're going through the cell, size doesn't matter. Okay, so your size is irrelevant. Now, that means small water-soluble substances are going to undergo diffusion. Small, medium, large lipid-soluble substances are just going to go through the cell. But what do we do about large water-soluble substances? How do we get those guys to and from the cell, or to and from the blood? Well, they employ transcytosis. So again, this is going to be employed for large water-soluble substances. Now, transcytosis is going to be coupled endocytosis followed by exocytosis. Okay, so what we see on this side is we have some type of receptor molecule. This receptor molecule binds to our target water-soluble substance. When the target binds to the receptor, it is incorporated into a vesicle. This vesicle then travels across the cell, where it then binds with the cell membrane on the other side of the cell, eventually expelling the contents of the vesicle into the fluid on the other side of the capillary. Now, this is energy expensive because endocytosis and exocytosis both require energy. But which is why it's only done for selective things, and it's why a receptor is necessary, because if there's no receptor, then then the substance isn't going to move. But for both diffusion and transcytosis, we're talking about the movement of specific solutes. But in many cases, it'd be much nicer and much easier if we could just move a crap load of substances all at once, irrelevant of what they are for the most part. And that brings us to bulk flow. Bulk flow moves a multitude of substances and solutes along with water into and out of the capillary beds. Now, this process is driven by pressure. So again, bulk flow is the movement of large amounts of dissolved or suspended materials in the same direction. Now, what we're going to see that's going to happen here is we're going to move some stuff out of the capillaries and some stuff back into the capillaries. And hopefully we do about the same amount. Now this pressure-driven movement of bulk flow is key when we want to talk about moving both solutes and water. And this becomes very important in maintaining the volumes of our body fluids, the ratio of how much water is in our interstitial fluid versus how much is in our plasma, etc. Now, as I just mentioned, fluid is in general going in two directions. It's either coming out of the capillaries or going back into the capillaries. As such, we have two different terms. Filtration is when the fluid is moving from the capillary to the interstitial fluid. IF is now my abbreviation for interstitial fluid. Reabsorption, on the other hand, is moving from the interstitial fluid back to the blood. Okay. Now, whether this is occurring is going to occur again in terms of pressures. But here's the thing, we've got multiple pressures, each pushing things in different ways. You've got some things that are pushing fluid out of the capillaries, some things pulling fluid out of the capillaries, something pushing fluid back into the capillaries, some things pulling fluid back into the capillaries. So with all of this pushing and pulling, who's to say what's going to happen when? And that's actually what is described by your net filtration pressure. Your net filtration pressure takes the balance of all of these pressures, and whichever one is highest, okay, whether the filtration pressure is highest or the reabsorption pressure is highest, whichever one is highest, that determines what is actually happening at any one moment. So let's take a closer look at these processes, or these pressures. Now, as I had mentioned, there are multiple pressures coming into play, but they are categorized as either a hydrostatic pressure or an osmotic pressure. Now, hydrostatic pressures can be simply described as a pushing pressure. When water or a solution of any kind is confined into a space, it's trying to push its way out. The degree of confinement, okay, the more confined the water is to its space, the higher the hydrostatic pressure. Okay. Now we have two hydrostatic pressures. Because we've got two fluids. We've got the fluid or solution in our blood, so we have blood hydrostatic pressure. And of course the other fluid we have is interstitial fluid. So we'd have interstitial fluid hydrostatic pressure. Okay. Now the other type of pressure is going to be our osmotic pressure. Osmotic pressure is kind of like the pressure to dilute. Okay. Whenever two fluids are separated from one another, and those two fluids are a solution, water wants to balance out the concentration of those two solutions. So water is going to move towards the solute, the higher solute concentration, and the degree of difference between the solute concentrations of those two solutions determines your osmotic pressure, which is why I like to describe osmotic pressure as a pulling pressure. Since the solutes are pulling water into the solution. Now, like we had a hydrostatic pressure for our two different fluids, we also have osmotic pressures for our two different fluids. So we have our blood colloid, osmotic pressure, and our interstitial fluid. osmotic pressure. Now from here on out, we're going to go ahead and use their abbreviations, which is BHP for blood hydrostatic pressure, IFHP for interstitial fluid hydrostatic pressure. We have BCOP for blood colloid osmotic pressure, and IFOP for interstitial fluid osmotic pressure. So now the question becomes, which one of these drive filtration versus which one of these promotes reabsorption? Remembering, filtration is going from the capillary blood into the interstitial fluid, reabsorption from interstitial fluid back into the capillaries. So let's think about this. Remember, for each of these, let's start with BHP. So here's our capillary, right? And this is, of course, all of our interstitial fluid out in this manner. Now remember, BHP is a pushing pressure, and we're in the blood. So we take our starting point here and we push, and we're going to push away from it, which means we are going from blood to interstitial fluid, which means this is going to be a filtration pressure. Okay. Next, we have interstitial fluid osmotic pressure. Draw our little capillary. Now our starting point is in the interstitial fluid, so we'll put our little dot up there. And remember, interstitial fluid osmotic pressure is a pulling pressure. Well, if osmotic is doing the pulling, we got to draw the arrow towards it. So again, we are going from blood to interstitial fluid. So again, this is going to be a type of filtration pressure. Okay. Opposite of that would be our other two, BCOP. So let's draw our little capillary. And remember, we're in the blood, so we put our dot there, we put our starting point there. We're in osmotic pressure, that means we're pulling, so we got to draw the arrow towards the starting point because we're pulling things towards the blood. So now we're going from interstitial fluid to blood. So this would be a reabsorption pressure. Lastly, we have our interstitial fluid hydrostatic pressure. So our starting point is in the interstitial fluid, which we see here. Interstitial fluid, hydrostatic pressure is pushing, so we take our dot and push on the capillary. So again, we're going from interstitial fluid back into the blood, which means we are reabsorption. So now we see we have two filtration pressures here with BHP and IFOP, and we have two reabsorption pressures with BCOP and IFHP. Okay. Now we got to look at it as to see what's happening, because none of these pressures exist in a vacuum. They're all interplaying with one another, all interacting with one another at the same time. So what we end up doing is adding up all of those filtration pressures and adding up all of the reabsorption pressures and subtracting the reabsorption pressures from the filtration pressures to see what's going on. And this becomes our net result. So let's get another blank screen. Okay. So what we end up saying is that if we take our net filtration pressure and we basically take our filtration pressures and add those up, and then we subtract our reabsorption pressures, we end up with our net filtration pressure. Now, if we want to keep this simple, what we see is if our filtration pressures are greater than our reabsorption pressures, that means our net filtration pressure would have a positive value, which means filtration is what would be occurring. So anytime our net filtration pressure is positive, filtration is occurring. If, on the other hand, we take our net filtration pressure and we see that filtration is less than reabsorption, Well, that would mean the end result would be a negative number, and and then reabsorption would be the end result. Now, your book demonstrates this principle very simply by taking a snapshot of what's occurring on the arterial end and taking a snapshot of what's occurring on the venual end. On the arterial end, we see that we have a BHP of 35, BCOP of 26, an IFHP of 0, and an IFOP of 1. Well, if we take and plug these values into our net filtration pressure equation, what we would see is we would take all of our filtration pressures, which is BHP plus IFOP, and subtract our reabsorption pressures, which would be BCOP plus IFHP. Okay, well, with that in mind, let's plug our numbers in. We've got 35 plus 1 minus 26 plus 0. This equals 36 minus 26, and we have a value of plus 10. So at the arterial end, we've calculated a snapshot filtration pressure of plus 10. Couple of things I want to note about this. First, you might have noticed this IFHP is 0. You might be asking yourself, why do I care about the number if it is 0? Well, remember what I said. Hydrostatic pressures are pushing pressures. And those pushing pressures arise when fluids are confined into a space. But for the most part, does interstitial fluid have much confinement to it? Or is the fluid just kind of allowed to go wherever it wants? Well, hopefully you're thinking it's allowed to go wherever it wants, which means if there's no confinement, then the fluid will go wherever it wants and there's not a lot of pressure to it. In actuality, it's not really 0 per se. What it is probably a very small decimal point of 0.00142, etc. But so, it does exist. It's just such a small number for our intents and purposes it's irrelevant. Does that mean you should ignore it? No, you shouldn't ignore it. You do need to know it exists, but just realize for our intents and purposes we can simply say that it's 0. Now, your book then takes and does the same type of measurement at the exact same spot, but on the venule side. But on the venule side, what we see what has happened, what we see that has happened is since we've gotten further away from our heart, our blood pressure has dropped more. So now by the time we get to the venule end, our BHP has dropped to 9, or not to 9, sorry. You'll see where that number comes from here in a minute. Dropped to 16. Now, BCOP, blood colored osmotic pressure. This is the pressure of all of those solutes within the blood. But it's primarily due to the concentration of plasma proteins. Because remember, plasma proteins are too big to leave most capillaries. So if they're too big to leave most capillaries, they're going to be the solutes that are going to get most concentrated in the blood when capillary exchange occurs. Well, here's the thing though. Did the number of plasma proteins change? No, the number of plasma proteins did not change between the arterial and the venule end because they weren't allowed to move. Well, if the number of plasma proteins didn't change, then the osmotic pressure should not have changed either. So that stays at 26. IFHP. Again, we don't really care what this is. We know it's a very small number, but we need to know it exists. And for the same reason, remember, your osmotic pressure didn't change. For the blood, it's also not going to change for It's also not going to change for the osmotic fluid either. So now let's plug in our new values. Net filtration pressure equals okay, so our equation is the same. Let's plug in our new numbers. So we got 16 plus 1 minus 26 plus 0. So we got 17 minus 26, and we get a value of negative 9. And since it's a negative value, it is net reabsorption. Whereas over here, it being a positive value, it was net filtration. Now, the way your book represents this is similar to what is seen in this diagram here. We take a snapshot of what's happening at the arterial end, and we compare it to a snapshot of what's happening at the venual end. And what we see is the two numbers are almost equal. And you should have noticed that from our calculations earlier. That means we filter at a value of plus 10, we reabsorb at a value of a value of minus 9. So what that means is we should reabsorb almost everything that was filtered. So again, the numbers are so close that we reabsorb almost everything that is filtered. Almost, though, is the key, okay? So what we see is about 85% of what's filtered gets reabsorbed. Almost everything. But because there's a slightly higher filtration pressure than reabsorption pressure, about 15% gets left behind. And the 15% that is left behind is returned, there we go, to the veins, so to your circulation by the lymphatic system. So here we learn of a new important function of the lymphatic system that most students aren't familiar with, and that's its function in returning fluids to general circulation. Returning some of our fluids, I should say. Now, this idea that most of what is filtered gets reabsorbed was originally described in Starling's law of the capillaries. Okay, and this is the same Starling from Frank Starling's law of the heart we see here. Now, the only problem I have with this description and this representation here is students tend to think that if we draw this magic line down the middle here, that we're plus 10, we're filtering at plus 10, plus 10, plus 10, plus 10, plus 10, and all of a sudden, oops, minus 9, minus 9. When we reach the middle, we switch to minus 9, minus 9, minus 9. Now, that is not actually accurate. Okay, because what's going to happen is our filtration pressure is slowly going to drop until we get to about the midpoint, at which point it switches and our reabsorption pressure slowly goes higher, which is why I prefer to describe this process more graphically. Now, even though we have 4 of these pressures, what we notice is the only 2 that are really that significant is our blood hydrostatic pressure and our interstitial fluid osmotic pressure. Our blood hydrostatic pressure and our blood colloid osmotic pressure. So what I like to do is make a little graph. And down here we can put the arterial end of the capillary is on one side of the graph, and the venule end of the capillary is on the other side of the graph. And then up the other side we have pressure. And then we draw two lines. Let's try some different color here. Let's take and draw our blood hydrostatic pressure, or our blood colloid osmotic pressure first. And remember, that value is a value of 26. But it's a 26 at the arterial end, and it's a value of 26 at the venule end. So all we need to do is draw that baby across. Now let's draw our reabsorption pressure. Our blood hydrostatic pressure. Remember, our blood hydrostatic pressure started up here at 35, but ended up down here at 16. Well, we connect these, and that's our line for BHP. Okay. Whereas this is our line for BCOP. Now, what we see is two general regions have arisen. In this area here, what we see is that BHP is greater than BCOP, so we have net filtration taking place. Okay. Whereas over here, BHP is less than BCOP, in which case it is net reabsorption. Now what you'll notice is when you take a look at these values, if you actually took and added up all of the filtration that occurred here and compared it to all of the reabsorption that occurred here, they would be almost equal. And that's the true definition of Starling's law of the capillaries, is that the total amount of filtration that occurs when BHP is larger than BCOP will be approximately equal to the total amount of reabsorption that occurred over here when BHP was less than BCOP. Now, ideally, this occurs normally throughout your life, but if any of you have ever experienced swelling for different reasons, and this, of course, is swelling not necessarily related to an injury, just fluid retention, that's referred to as edema. And edema is simply the increased accumulation of interstitial fluid, or the increase in the volume of your interstitial fluid. Now this occurs anytime your filtration pressure is higher than your reabsorption pressure. Now this can result for two reasons. You could have excess amounts of filtration that causes the increase in, or the ratio to be out of balance, or you could have lower than normal reabsorption pressures. So let's see if we can figure out when this might occur. Starting first with excess filtration. Well, remember, the driving force for filtration is BHP. Well, for it to have excess filtration, BHP would have to be higher than normal. Now, this is going to occur anytime you have an individual that's suffering from hypertension. Okay. In this scenario here, if we draw our graph similar to what we just drew on the previous page, right? This is what was normal, right? Let me make more room here for a better graph. Okay, so now I have a little more room for my graph here. Well, remember what you saw previously. Well, if BHP is the cause, then our BCOP is still up here at 26, But now our BHP is higher than normal. So instead of starting at 35, we're starting at 45, and we're getting to 26. Well, now we see a vast difference in the amount of filtration that's occurring compared to the little bit of reabsorption that's occurring, which means we're leaving more fluid in that interstitial, leaving more fluid in the interstitial fluid, and the volume is going to increase. Now, this inequality can also occur due to inadequate reabsorption. Now remember, the primary driving force for reabsorption is BCOP. So if it's inadequate reabsorption, then BCOP must be lower than normal. So if we take and draw our graph and to explain this, in this case, our BHP is fine. So we're at 35 here, we're at 26 here, or excuse me, 16 here, and we draw our line like that. But now, if our BCOP is lower than normal, well, if our BCOP is down here at 20 instead of 26, again, we have the same problem. Not a lot of reabsorption to combat all of this filtration. The question is, why would BCOP be lower than normal? Well, remember, BCOP is due to the concentration of our plasma proteins. Well, if it's lower than normal, then we have a lower concentration of those plasma protein. Well, what's causing that lower than normal plasma proteins? Well, one option is you're not making enough. Which would be true if you have liver failure or liver problems. Another option is if you're losing too many, when you shouldn't be, and this often occurs with kidney problems. Okay. Now, remember, we normally leave a little bit of extra fluid behind in the interstitial fluid, and it's not noticed because of the lovely lymphatic system. So that lymphatic system is actually pretty robust. It normally handles 15%, but it can up the ante to handle about 30% excess interstitial fluid. So if either of these two things are a problem, we typically won't notice until the excess interstitial fluid accumulation exceeds 30%. Up until that point, the lymphatic system is picking up the excess. So let's see how we're doing with this second lecture with some Do You Get It questions. Remember, as I go through these, I might be going too quick for you, so make sure you pause the lectures while you read them and come up with your answer. So which statement is true about capillary exchange? Interstitial fluid hydrostatic pressure pushes fluid from the capillaries to the interstitial fluid. Blood hydrostatic pressure is lower at the venous end of the capillary. Blood colloid osmotic pressure is primarily due to dissolved ions. Filtration is the movement of interstitial fluid into the capillaries. Blood hydrostatic pressure is caused by the elasticity of large arteries. Well, picking through these and thinking about each of them, one of the ways in which you can deal with a question like this when you come across it is dissect each statement and see if you can find what's true or what's false about it. If you've done that, then you should have highlighted the fact that B is your only correct answer. The first one, interstitial fluid hydrostatic pressure pushes fluid from the capillaries to the interstitial fluid. Well, remember, if you're an interstitial fluid hydrostatic pressure, then your starting point is the interstitial fluid. So we would need to reverse these twos to make this a true statement. It's going to push fluid from the interstitial fluid back into the capillaries. Okay. Blood colloid osmotic pressure is primarily due to not dissolved ions, but as we just recalled, plasma proteins. Fluid movement from capillary, from interstitial filtration is the movement of fluid from interstitial into capillaries. Of course, we know that is not true. That would have to be reabsorption. Finally, blood hydrostatic pressure is caused by the elasticity of large arteries. Well, what the heck does large arteries have to do with anything to do with capillary exchange? The blood hydrostatic pressure is actually entirely due to the contraction of the heart. Okay, so let's go to our next question. Notice the double asterisks here, so here we got two possible answers. So take a second, read it, and see what you come up with. Okay, which of the following contributes to filtration? BCOP, BHP, IFOP, IFHP. Well, the two that contribute to filtration are going to be BHP and IFOP. What you want to remember is with your net filtration equation, if we write it out down here, we have BHP plus IFOP minus BCOP plus IFHP. Okay, notice each parenthesis has a hydrostatic pressure and an osmotic pressure, and each parenthesis has a blood, and each one has an interstitial fluid. So that might help you remember this equation. One last thing I wanted to point out, just to remind you guys of some rules of math, which for some reason many of you forget, but I've had students in the past not be able to pick out the fact that this equation here is identical to this equation here. Now the only thing we simply did was distribute this negative sign through the parentheses. But that got students confused and they thought things were wrong. So I just want to kind of highlight you and remind you of that thing, that these two are identical. Okay. Next question. True or false? All fluid filtered from the arterial end of the capillary is reabsorbed into the venous end. Well, this is false. It's true for most definitive statements like this, but to make this a true statement, we would have to do most, or about 85% to make this a true statement. Okay, that brings us to the end of our second section in our second lecture. By all means, if you're confused about anything, reread this section or email me with your questions. See you back here for the third topic.